It's a crazy day, everything else. So first off, thank you for you guys are just kind of acting like normal, not anything weird with the crazy day or anything else. But probability is normally something we don't get to till the spring. So I hope you guys are at least having some enjoyment. Might be a stretch. I don't know if most seventh graders enjoy when we do the math. But these things are like fun to think about, right? And figuring out how I can anticipate what's going to happen is actually something adults have to do every day. And one of the things that has happened is probability played into everything that has happened today. Anyone explain what I might mean by that? That probability. Look at Marvin. His hand is up. Marvin.
That like the probability of the weather, like if it's gonna rain and ice and
What's the probability of the weather? What's the probability of snow? What's the probability of when it gets here? What's the probability? There is so much probability at play right now that you're going home at noon because we won't risk the side of the probability that something bad happens, right? That's the other side. There's the probability, okay, we do it early, we miss it, we get you home beforehand. So realize, like, probability is a part of the everyday life. And beyond that, when adults are driving and everything else, what's the probability I will slide when I hit my brakes? What's the probability I will, like, go around this corner? So it's always going in your head. So this stuff's really important. So yesterday we talked about probability tables, right? Was anybody at Cosine on Wheels and missed our class yesterday? Okay. So make sure we get notes from a friend. Videos up on YouTube. But now we're going to talk about probability trees. So if you could please put a header in your notes that 525 is probability trees. And please emphasize. Oh, I need to reorient this. Please emphasize that we're making trees. Did you guys do any, and this might be dangerous fast, did you guys ever do like factor trees or any kind of other trees as models? So, the main time, or really, the questions you want to ask yourself leading to, do I use a probability table, do I use a probability list, do I use a probability tree, is, are there more than one event? Right, we saw yesterday if there's two events, a probability table is really nice. Do both one event and the other events occur? And are the events independent or are they dependent, right? The one impacts the other one. So yesterday, one of the situations I think we talked about near the end of class was coin flip and dice roll. We made a little table with the dice roll on the top, 1 through 6. Coin flip on the side, heads and tails. We looked at there were 12 options there. But what if we're going to do a dice roll, a coin flip, and then a rock, paper, scissors? Or a dice roll, a coin flip, and pick a block from the bag. Right? We've had those problems with. So now we have 3 events happening. Ponder that for a minute. What would you do with 3 events? So we're going to talk about problem 65, the double spin. So we're going to play a game again. This whole chapter is about games. So our wheel is divided into 5 sections, as you can see. And we've got the numbers labeled, as you can see. And we're going to spin 2 times. The sum of our spins determine whether you win. So work with your teammate to determine what you think about the list of possible sums, what sum you think will be most probable, have the highest probability, and create a probability table that shows this. So this is very similar to rolling a die, right? We have 5 options now and 5 options. So set up your probability table, the 5 options across the top, the 5 options across the side. Inside the table is going to be the sum, right? We're going to add these. If you have a question, stick up a hand. Otherwise, take a couple minutes to work on this. Try to answer those 4 questions. If you're struggling at all, remember this is how we set up our table. The one event on top, the other event on the side. Both of our events here are spins. So we just label it spin 1, spin 2. Then as you fill in inside your table, it's these sums. Now I put mine in order from least to greatest, -2, -1, 0, 1, 3. You might have a different order. If you have a different order, your table is going to end up differently. So, if your table is exactly like mine, you can check as I fill in that yours matches. If yours isn't set up exactly like mine, yours won't come out to be exactly the same. You'll end up with the same numbers inside, but they'll be arranged differently. So keep working on your paper. If you need to check, look up here. We may not match exactly. Bless you. Something that you guys can see. Always make sure that I'm correct, because I make mistakes. I've been known to be wrong. So I think this table's correct. Now, even if your table's set up differently, you will have the same numbers inside. They just might be arranged slightly differently. What's the lowest sum that we can get here? That went up, went down. Delaney? -2, that's the lowest. Not lowest probability, I'm just saying lowest sum. Ella? -4, right? So actually, in how my table's laid out, it ends up being top left. And the highest sum, because I laid out my table lowest to biggest and lowest to biggest, my highest sum comes down here at the bottom right, because that's where my biggest and my biggest add. We get 6. Now if we ask, what's most probable or least probable? So, B asks, what sum do you think will be most... Now we could do A. We could list all the outcomes, depending on how much time we have. I'm trying to move a little bit quickly today. But what do we think will be most probable, and how do we know this? So, Mr. Cooper, what do you think? What do you even do to figure out which one's most probable? See which one appears the most time, so find matches probably, right? What do we think? Anyone have a guess of what appears the most? Numbers are kind of all over the place. Patrick, what do you think? -1. -1. So let's find out how many -1s we have. We have this -1, this -1, this -1, and this -1. So we got 4 of those. Any other number? We've got other numbers that appear multiple times, right? -3, -3. -2, -2, -2. Ooh, You notice a pattern kind of like what we saw yesterday? Depending on the row, we have those diagonal matches. Right, I'm checking my math. -1, -1, -1, -1. Yeah, that's right. Why does this diagonal get goofed up? Anyone know why that diagonal, Alan?
Because the 3 at the end is 2 more than 1.
Ah, the gap here is not consistent, and the gap here is not consistent with all of the other steps. Up 1, up 1, up 1, up 2. That's why this diagonal gets goofed up, and the rest of the table is kind of what we saw yesterday. So yeah, the -1 appears the most. So in your notes, let's write probability of. How do we show probability of? L? Ooh, I was waiting for that. So let's do -1 first, then we'll come back to the 1. So Eleanor, how do we show probability of something? P with a parenthesis, then what goes in the parenthesis? You keep on if you want. -1, the event that you're looking for, right? So we say probability of -1. How many of that were there? How many outcomes were -1? 4. So my numerator is 4. How many we have? How many total outcomes do we have? Careful.
Good morning. Ellie and Alex Koenig, please stop by the office for a message. Ellie and Alex Koenig, please stop by the office for a message.
So the class answers on this. How many options for spin 1? How many options for spin 2? For spin 2, they're still on the 5. 5 times the next 5 makes, what's 5 times 5? 25. So a few of you said 30, which kind of scared me. Multiply how many options times how many options? 5 times 5. So it's 4 out of 30. Can this be reduced or simplified? Can I divide my numerator, my denominator by the same thing?
4 out of 30.
4 out of 30.
4 out of 25.
Thank you. Can that be reduced? What? No, not necessarily. Now I do it a whole lot more. The further we get in the year, the more that I try to make intentional mistakes and see if you guys are paying attention. So 4 out of 30 would have been reducible. Can I reduce 4 out of 25? Can they both divide by the same thing? No. They can't divide by 2 because it doesn't work for 25. Can't divide by 4, doesn't work. What if I wanted to talk about this as a percentage? Why? If I can get the denominator to be 100, I can talk about percent, right? What do I multiply to get there? 4. What's my numerator?
16.
So what's my percent?
16%.
16%. Please jot that down. We got to be really good at fraction, decimal, percent conversions. That just needs to kind of be fluent. Percent out of 100. So, who was it that told me 1 has, was it Ella? Ella, so 1, they're not together, which makes it a bit more difficult to see. I hate that I don't have very many highlighter colors. Let's go purple circles. So a 1, a 1, a 1 down there, a 1 up there. So it is 1, which is most probable, 1 or -1? Oh, they're equal, right? So they have equal probabilities. Probability of 1 is the same as the probability of -1. So you can just throw on there, oh yeah, probability of 1 is the same also. Because there are also 4 out of 25. All good? Preguntas. What's the least likely up here? Same. Grant. The 6 or the negative 4. Because each of them have a probability of what? So the probability, let's just say, of 6, be 1 out of 25. Now, can we mentally figure out what percent that would be? What would it be? 4%, right? If I have to quadruple this, I'd have to quadruple that. If we want to talk about percentages, it only has a 4% chance of happening. So the reason we have an early release today is the percent chance of the bad weather is really high. If you look at Weather Underground, which is the app that I use, it says 100. Right? 100% means it's happened. And then there's another that says 90%, which is essentially meteorologists saying, like, yeah, it's gonna happen, but we'll hedge our bets. Right? Leave a tiny little window where, well, we said it was 90%. Right? But 10% chance it won't happen. School districts won't bank on a 10% chance. They're gonna trust the 90. Questions on the table? Now, what happens if we spin this a third time? Can I just like extend my table and... So, if one option, one event, I just could make a list. Give me your eyes up here for a second. 2 options, I can make a table. 3 options, this might be a little deep for you guys. We'd have to represent with a 3-dimensional model, right? We went from a list to a table. Now if we had a third, how would that work?
Or we could just make a list again.
Ooh, kind of, yeah. We make a probability tree. So, and I think we could all answer D. Hey, if you want Tabitha to win, should she choose higher probability, lower probability? Higher. So choose what number? Negative 1 or 1. Either of those have the same chance of winning. So, we're going to change the situation so it makes more sense to you. As opposed to doing the same thing over and over again, we are going to go get ice cream. Nothing better on a snow day, or, well, not snow day, but like in icy weather than going to get ice cream, right? So, in, who's ice cream? Scott's ice cream shop, Crazy Creations. Anyone ever been over to the place in Worthington Mall? Cookie Dough Creamery. So, hold up. So this is slightly different. I gotta relate it since Cookie Dough Creamery is local. Anyone ever been to Cold Stone? Okay. What's the difference between Cold Stone and Cookie Dough? Ella's using her hand. Yeah, Colleen?
One of them, there's like cookie dough, like on it, and you get to like put whatever ice cream you want on it, and you just pay for the cup.
Okay.
And then the other one, you just get a limited amount of ice cream, a cone, and a couple of scoops.
And do you mix your stuff in at Cold Stone?
No.
No, they do it, right? So this is like Cold Stone. You tell them an ice cream type. You walk down the line. If you've never been to Cold Stone, it's pretty cool because they literally, it's operating on a cold stone. That's how they got their name. They then pull out your mix-ins, mix it up. If you want more mix-ins or a fruit thing, or they go down the line, they get that, they mix it in, and then they give you your ice cream. Right? So you make the choices, but they do it. So this is what we're doing. We're going to choose chocolate or vanilla. We're going to choose hazelnut sprinkles or toffee bits. We only get to choose one. Sorry, guys. And then fruit, we get a fruit swirl to go in. And I had the question in my other class, so no, you cannot say, well, I don't want a fruit swirl. We're going to choose one from each. The question is, how many different ice cream creations do you think can be made? So first, without talking with your teammates, Kate, without talking with your teammates, how many combinations do you think there are? Take 30 seconds to think about that, then I'll let you talk. without writing anything. Talk with your partner. Do not write anything. Just talk with your partner. What?
We were counting.
What? Ah! Ah!
I forgot what it was.
I did not. These shoes are great. It looked like I did. But... Okay, so what? You want this?
Yes.
Why do I think this? Pink should always be. Fine, I'll copy that out. I'll leave it up on the TV, but I am doing this. All right, everybody, in your notes, you need probably at least like half a page. So if you don't have half a page, flip to a new page or the back of a page. I need you to write Crazy Creations or ice cream or whatever you want to say. But I'm going to write Crazy Creations. When you walk into Crazy Creations, would you first tell them, hey, I want an apricot fruit swirl? But apricot's an option, or apricot, depending on who you are. No, you start with what? What do you do first? Choose an ice cream, right? Base flavor. So, Allie, what are your options? Yeah. 2 options, right? Vanilla chocolate. So, first thing you do is choose your base, and that has vanilla or chocolate. Now, I prefer to make my probability trees vertical. The book, and I might give you this resource page next week, but it's kind of a pointless resource page. I just wanted to do this in your notes. You can do it horizontally, but a lot of times I run out of paper or I run out of space, especially up here. Now, does my choice of vanilla or chocolate affect what mix-ins I'm able to have? No. So if I choose chocolate, what mix-ins do I have to choose from?
Hazelnut, sprinkles, and
The 3, right? Hazelnut, sprinkles, and toffee bits. So it's still up on the TV. Don't hit me. So now mix-ins is the next choice. And that, for chocolate, has 3 options. Right, hazelnut, sprinkles, or toffee bits. Whether I get vanilla, it still has 3 options. Hazelnut. No, I said sprinkles in the middle over. If we stop here, how many possible ice cream options are there? Matt, what do you think? If we stop here, how many possible ice cream options are there? Close. Liam?
Can you mix vanilla and chocolate?
No. They're very strict about that. Nathan?
6.
How do you know that?
Because there's 3 on each. And there's 2 flavors.
When we're using a probability tree, to know how many total options there are, you just count where you've ended. So across the bottom where I've ended, there are 6 different things. What would this be? What does that T represent? Just toffee bits? Chocolate ice cream with toffee bits. This would be chocolate ice cream with hazelnut. Right? We come down the tree. Another way we can do this is the multiplication. There were 2 base flavors. There are 3 mix-ins. 2 times 3 equals 6. So go the next step. Try to build your tree, including the fruit swirl, and then determine how many total options there are. Why did you just reset? venture a guess for how many total options we'll end up with, Francesca? 24. What's 2 times 3?
6.
6 times 4?
24.
There are 24 options here. Now, as awkward as it might be, Annika, can you tell me what that G would actually represent? Oh, yeah. So this, that wasn't what I was asking, but that's awesome. The probability of this thing, that ice cream, we're not going to name it yet, but that would be 1 out of 24. But what we're asking is, what is that ice cream?
Vanilla ice cream with toffee bits and grapefruit syrup.
Yep, and that would be really good. That doesn't sound good to me. But vanilla with toffee with great, you just work down the tree. This is why probability trees are really nice. Instead of saying VTG, like we tried to make like a table to like, we'd have to say vanilla and then toffee and then. Instead, over here, we can just start to use single letters and then trace down the tree. And it makes life easier. Would there be a limit to how many different add-ons they could give us? Like, could they give us a second mix-in? And could we do that on the tree? Couldn't I just add a layer? Like, from this G, say, now they say, oh, wait, you also get your choice between chocolate sauce, caramel sauce, and strawberry. So then from here, we'd have to do chocolate or caramel or strawberry. From here, chocolate, caramel, strawberry. And it gets really hard to draw, but you can keep adding choices. So probability trees are limitless. That's why they're so useful. If you end up with a giant one, I got poster paper. So if you really want to make giant probability trees, I had a student one time say, well, how many choices can we, like, how many options could you give? It's limitless. You could really keep doing stuff. So one challenge would be like, how many different games could you play that could all tie together? Like flip a coin, heads or tails. Roll a die, 1, 2, 3, 4, 5, 6, like, and it just gets bigger and bigger and bigger as you go down the choices. I forget what we're doing next. I should really just open that book to the right page. Where's the fun in that? What is the probability that Scott will end up choosing something with plum? So take a moment. You can talk with your partner about this. We got about 8 minutes left in here. What's the probability he chooses something with plum? Nathan, what do you think?
6.
Well, 6?
Yeah.
That's not a probability.
Well then.
6 is just a number. Or probability has to be a fraction. I agree with your 6. 6 out of what? How many total options did we say we have?
24.
Gotta love the phone a friend over there. Now, what is 6 out of 24 reduced to? Might blow your brain here. Helena? Aren't all of my bottom sets the same? Like A, P, B, G, these are all the same. Isn't plum just 1 out of the 4 final options? So couldn't I just look at the fruit swirl step and say it's 1 out of 4? We can do this, but there's also an easier way. I'm here to make your life easier. What's the probability it'll include hazelnuts? Let me change the question and see if you solve it any easier this time. These are all hands that are. Delaney, we haven't talked much.
2 out of 24.
For hazelnuts? So at this, well, I agree with your 2, depending on how we're going to use it. At this layer of choice,
Oh.
when you're talking about 2, it's because you see 2 hazelnuts, right? But that's out of how many? 6. So 2 out of 6, what's that reduced to? 1/3. Oh, it's one of the 3 choices for mixing.
What is the sorcery?
Mathematics. Alright, yeah. Let's talk about another vocab word. So, mutually exclusive. We do want to write this because it's going to pop up in your homework and prep.
Good morning, Emma Browning and Delaney Marty. Please stop by the office for a message. Emma Browning and
They're just trying to
Delaney
mess up my
Marty,
math
please stop by
class
the office for a
even
message.
more.
Trying to scare me.
Alright, mutually exclusive. Hey, with me please. I only got like 5 minutes left. And we're going to say events. Mutually exclusive events. Because it'll make defining it easier. Mutually exclusive events. It means to be exclusive. They have no outcomes in common. Do we have that down? So I gotta go back. So Scott's sister loves hazelnut. Scott's brother loves grape. So here's a nice way to think about mutually exclusive. Could Scott's brother and his sister share one ice cream? So what can I get through for a minute? Scott's sister loves hazelnut. Scott's brother loves grape. Could they share an ice cream? Raise a hand if you can explain how you know. Allie?
Yes, they could because they're using that. It's one of the toppings,
Mm-hmm.
and then for the grapes, it's fruit swirl, and so they can both get the same thing.
Because they happen in 2 different steps. Exactly what Allie's saying. The hazelnut was up here. It was the mix-in. The fruit swirl down here is after that choice. I can have an ice cream that has hazelnut and has grape. Now let me change the situation. Scott, and I don't know if the book does this because I go rogue often. So Scott's sister loves hazelnut, right? Scott's cousin loves sprinkles. Could they share an ice cream? Liam? Why?
Because they're both on the same row and you can't mix them together.
If one path I take wants to choose hazelnut and then continue on, and another path that I'm going to take is going to choose sprinkles and continue on, do they have any common outcomes? No. This hazelnut path, this sprinkles path, they have no shared outcomes. They could not share an ice cream. So when you're thinking mutually exclusive means you can't share. No common outcomes. They don't agree. Questions? Sweet. So Rona is like stir crazy, kind of like me probably. The power's out, but yet Rona's gonna go organize her closet. So hold up. So she's gonna find one shirt, one pair of pants, or sorry, not organize, but we're gonna go get clothes, right? I would organize my closet. Sorry, there's another problem. This is the problem with me planning 3 classes at the same time because I teach 3 different classes. If you're not aware of that. No. Well, yes, I change clothes every time. No, I get confused problem to problem. So we're going to choose one outfit. Okay, so reset. We're going to choose an outfit. The closet's dark. Can't see anything. I'm afraid of it, so I'm just going to reach in and grab. I know by feel what's a shirt, what's a pant, and I think that's it. Yeah, one shirt, one pair of pants. We'll get more complicated later in the book. So, Rona's got 3 pairs of pants, one black, one brown, one plaid. 2 different shirts. Rona's a simple person. 1 white and 1 polka dot. So, we have about 2 minutes left. I'm going to quickly draw a probability tree. It doesn't matter which you choose first. You could choose a shirt and then choose a pants. You could choose pants and then choose shirt. But what's the probability she'll wear polka dot shirt and plaid pants, which would be a sweet outfit? That's what you're trying to answer. Who can help me finish this? What do I need to do now? Penelope, can you tell me what I need to do to finish my tree? Okay, how do I add the shirts?
Like for the black pants,
How many options are there for shirt? So we're going to draw 2, we'll say roots, right? If it's a tree, we're going to make roots. So we'll draw 2 more roots off of here, and the choice is white or polka dot. 2 roots off here, white or polka dot. And 2 roots off here, white and polka dot. Nathan, how many of these outfits involve the plaid and polka dots?
1.
Out of how many total outfits? Remember, the probability tree tells me, because these are the possible outcomes, and then I can trace it back. So you just count the bottom of your tree, and there's 6. So the probability that we have plaid and polka, so we can say PP, plaid and polka, I guess, is 1 out of 6.
Oh well.
And that's all we got. Thank you guys very much. Please do your homework over the weekend. I know it's Friday, but you have a 3-day weekend. You can get it done. It's just 71 to 75.
Wait, we have a 3-day weekend? Oh, yeah.
Monday's off.
No.
Again?
Oh, Tuesday's off.
Every
Okay.
Monday.
No, because after this Monday, we go into the long stretch of like endless winter.
I